Okay, let's start out with a sort of estimation problem that originates in the video clip you're going to see in a minute. So what you're going to see in a moment is a video of an earthquake in Tokyo from several years ago. And you'll see the top of a kind of dark colored building, a building with a very dark colored facade, swing back and forth like this. And I was trying to estimate both the amplitude and the period of oscillation. And the period is easy because you can basically just count the number of times it goes back and forth and count off seconds on a stopwatch. The amplitude is a little harder. The way I estimated the amplitude, and you could tell me if you get a different answer, but I said, well, one story, you can kind of tell from the pattern of the windows how tall, where a story is vertically, and a story should be like 3 or 4 meters, like 10, 12 feet. Then I said, okay, that's vertically, that's a story, so now I know horizontally what would correspond to like 3 or 4 meters, and then I'd say, okay, if I see it going back and forth, back and forth, back and forth, then from extreme to extreme is 2 times the amplitude. Since the cosine wave goes up to 1 times the amplitude and then back to 0 and then down to minus the amplitude and then back up to plus the amplitude. So extreme to extreme distance is 2 times the amplitude. So I said, okay, you know, the extreme to extreme distance in the video corresponds to something like half a story was my guess. So which would be something like 2. So an amplitude of about 1 meter. And then I estimated a period of about 4 seconds. So the reciprocal of that would be the frequency is about 1/4 of a hertz, so 1/4 of a cycle per second. And then remember our expression, amplitude times cosine of 2 pi times frequency times time. Now, if you're just sitting in this office building, then if you're not looking out the window, you're just sitting at your desk, maybe in the interior of the building, you can't really detect the change in position of the building, and you also don't really detect the velocity of the building. I mean, if you're riding in a train or if you're on a smooth car ride, you don't notice how fast you're going, but what you do notice is acceleration. If you change direction or if you speed up or slow down, you can feel that even with your eyes closed. So what you're going to detect in the building is the acceleration. So I said, okay, first derivative of the position versus time is the velocity versus time, and the next derivative is going to be the acceleration versus time. So this is our expression for acceleration that we used last week, minus 2 pi frequency all squared times amplitude times this cosine expression. So the biggest value you get for acceleration is when the cosine takes the value 1. So it's just, well, and also the magnitude, so we don't need the minus sign. So 2 pi times the frequency all squared times the amplitude is the maximum acceleration in magnitude. So we can I plug in a meter as my estimate for the amplitude and 1/4 of a hertz for my estimate for the frequency. And I put the numbers in and I get the maximum acceleration is about 2.5 meters per second squared, which is about 1/4 of a g, right? A g is 9.8 meters per second squared. So that's amazing, actually. That's a huge acceleration. So that would be very uncomfortable for the occupants of the top floor of this building. So I looked up some numbers. You can just barely feel accelerations that are about 0.005 g or larger. So that's like a 200th of a g or larger. And then you start to feel a little uncomfortable for accelerations bigger than about 0.02 g or so, 2% of a g or so. Putting this into, so 0.02 g is 0.2 meters per second squared. So 0.2 meters per second squared starts to feel somewhat uncomfortable. This is 2.5 meters per second squared. This is like more than 10 times that threshold. So I would say this would be very uncomfortable for the building occupants. I'd say the people that you're watching, if there's anybody up there at the top story of that building, of course, you know, it's going to be a smaller effect down to the lower floor, but if you're up in the top floor of that building, moving with that big amplitude, I think you're going to find that really uncomfortable. So then keep that in mind as you watch the video for about 10 seconds, and then we'll go on from there. This is a contraption we call the transverse wave machine. If you have a long chain of things that behave like oscillators when their next door neighbors are held fixed. So if I take one of these, I hold this thing fixed, and I hold this thing fixed, and I let this one oscillate. You see it oscillates back and forth. These are like a whole bunch of coupled to their next door neighbors oscillators. So this thing is like a little mass, and there's a little spring between it and its neighbors. So it'll oscillate up and down. So it behaves like an oscillator when its neighbors are held fixed. If I move one of these things, its neighbor will move proportionally to how much it moves. You want it to be like an oscillator by itself, and you want it to interact with its nearest neighbors, so that if I move and my neighbor is motivated to move, it also has to behave linearly. So if you have such a thing, that's a medium in which waves can propagate. And waves, you know, they kind of have a nice aesthetic. This thing, if you look down on it, there's a long piece of thick piano wire going down the axis like a spine, and then perpendicular to that are a bunch of metal rods, and then on each one of those metal rods is like a little dumbbell with an equal weight on each side. The piano wire is trying to return each one of these to the horizontal position. And if two neighbors are misaligned a little bit, then a restoring force tries to realign them. We also have a little glow-in-the-dark sticker on the end of each one of these dumbbells. And we have an ultraviolet light, sometimes known as a black light. The first thing to notice is that this medium, we've created the medium with this set of coupled oscillators, it has a characteristic physical property called a speed of wave propagation. So if I make a pulse here, you'll see that pulse propagate down and come back. And I can make a somewhat different looking pulse, but it'll still propagate at that same speed. So this speed at which the disturbance propagates down the chain is a property of the medium. In the simple case that we study most often, that property is just a constant. There are some more complicated media called dispersive media where that speed of wave propagation is a function of the frequency, but that's a more complicated case, so we're going to deal with the case where the speed of propagation is a constant. Waves can be either transverse or longitudinal depending on whether the direction in which the disturbance propagates is the same direction or a perpendicular direction to the direction in which each little particle of the medium is moving. So in this case, if I create a disturbance, the disturbance moves horizontally, but each little piece of the medium is moving vertically. So these are transverse waves. We can make a pulse propagate as a wave down the medium. And then you can see interesting things happen at the end. We'll get to that in a moment. Or we can make periodic waves. So if we make a periodic wave, we can make one end go back and forth at a fixed frequency. And then eventually, after the kind of initial transients die out, you get a nice, this looks like a standing wave. It's kind of the same pattern again and again. And now notice if I shake it more slowly, lower frequency, we're going to see a longer wavelength. It takes a while for the transients to die out and for it to reach a new steady state. But if I shake it more slowly, you're going to see a longer wavelength. And if I shake it more quickly, you're going to see a shorter wavelength. Again, we have to wait for the transients to die out a little bit. So I shake it higher frequency, each piece is going up and down more times per second. We see a shorter wavelength. Lower frequency, so each piece is going up and down more slowly. We're going to see a longer wavelength. The ideal thing that a wave wants to do is to propagate forever down an infinitely long string or an infinitely long wave machine. If you shout into an open field, there's no echo, so it kind of wants to do this and just keep going forever. But sometimes the wave runs into an obstacle. So there are basically three cases that we can study easily. One is that the far end is totally free. The other is that the far end is totally immobilized. And then the third is that there is a perfect energy absorber on the end so that the wave thinks that it's traveling down an infinitely long medium. That third case is kind of hard to arrange, but we can get pretty close. So right now, the far end is completely fixed. It's immobilized. So then when the wave reaches the far end, it's going to come back with the opposite sign. And the reason why that makes sense, that it comes back with the opposite sign, is that for that point to be immobilized, the original wave and then the new wave that comes back, at the instant when they're both present at the end, they add up to 0. So it's as if you have the wave coming in plus the wave that goes back, and they cancel each other out perfectly. So that makes sense that they have opposite signs. So it goes up and it comes back with the opposite sign. It goes up and then it's going to come back with the opposite sign. Yeah, that's pretty cool. If we make the far end be completely free, so if we disconnect the mass from the far end, so then the far end can just wave in the breeze, it's kind of like shaking a rope and the far end of the rope isn't attached to anything, then you'll see the pulse come back with the same sign. And actually at the instant when it's reflected, it'll be double the original amplitude. So you see it come back with the same sign. So if the beginning is up, then the beginning will be up again. So the front part is up, the front part is still up. The first part is up, the first part is up. Good. At the far end here, we studied two cases already. One was that the far end is completely clamped, it's immobilized. It's not going to move. So then when the pulse reflects, the reflected pulse has to have the opposite sign so that the two pulses add up to 0 here. The other case was this thing is just free to go up and down. In that case, the reflected pulse has the same sign as the original pulse. And it turns out, if you like math, that the constraint turns out to be that the slope of the wave is 0 at the far end, but you don't have to remember that. And now the third case that's interesting is if we put what's called a dashpot at the end, and this absorbs all of the energy that comes in so that the wave thinks that it's propagating down an infinitely long string or wave machine and no reflection comes back. Yeah, that's pretty good. So there's a tiny little reflection because it's hard to make a perfect energy absorber, but that's pretty decent. So let's do it again. Yeah, that's pretty. You even hear the little. You might be able to hear the little swishing sound from the water. It's basically a little pot filled with water. So there's the wave. You just hear a little splash, and the wave basically dies out with a very minimal reflection. One weird property of waves is that two waves can pass right through one another. So if you had two particles going in opposite directions and they went through the same point in space, then they would probably, unless they missed, but they would basically bounce off of one another. They would both be affected by this interaction. But if you have two waves traveling in opposite directions down the same wave medium, actually they can pass right through each other undisturbed, except that during the time interval when they overlap, their amplitudes add. So Bill and I are going to send positive pulses toward each other at the same time, and it's really interesting when they meet. That's pretty cool. There's a reflection after they bounce off of the far ends, but at the instant when they meet, notice that the amplitudes add, and you get something in the middle which is about twice as high as the original. Let's try it again. Yeah, that's really neat. So you can see what appears in the middle is like the sum of the two original waves. Okay, these are some wave animations that I made with a little Python program, the Python version of processing. So you see that was a positive pulse coming from the left, an equal sized positive pulse coming from the right, and when they overlap, they interfere constructively. Now you're going to see a positive pulse coming from the left and a negative pulse of the same size coming from the right, and they're going to interfere destructively while they overlap. And then you're going to see two pulses of different size. So they differ by a factor of 2 in size. You'll see them overlap. It's more interesting to see what happens when they have opposite signs. So next you're going to see two pulses of opposite sign and differing by a factor of 2 in size. So then they do not cancel quite completely while they overlap. Cool. Now, what happens if I send a positive pulse and Bill sends a negative pulse? They should add to 0 at that instant when they overlap. Cool, yeah. Okay, that's kind of cool. Yeah. Yeah. Let's try to get some standing waves going of...
Pretty good standing waves before.
Yeah. Okay, so there we have what, 1, 2, 3 full waves on the machine. That's pretty good. That's a pretty nice sine wave where we have approximately 1 complete wavelength on the wave machine. One, 2, 3, 4. Looks like between 5 and 6 complete waves on the machine. There, 1. I don't know, roughly 5 waves on the machine, I think. Cool. And you can see that the wavelength is pretty long. It seems like about, I don't know, I would estimate about 1.5 waves fit on the machine. Now I can shake it at a higher frequency. And we should see a shorter wavelength. And again, you can see that the wavelength is shorter because a larger number of waves, or a larger number of fractions of a wave, appear on the machine. Now let me shake it at a higher frequency yet. And again, you'll see that you can see a larger number of waves. And then I'll try to go even to a bit higher frequency. And you clearly see a larger number of waves on the machine. And then even a higher frequency, and this is definitely a larger number. Let me see if I can go a little bit higher. That's pretty decent. And you can hear the frequency at which I'm shaking the end. You don't really hear it where I'm shaking it, you hear it where the wave reaches the little can of water on the far end. Okay, and then I'm going to reduce the frequency gradually. This is the transverse wave machine. Transverse in that each little piece of medium is moving up and down, but the disturbance propagates from right to left. A moment ago, you saw transverse waves. So the disturbance was propagating horizontally, but each little piece of the wave machine was only moving vertically. So that's called a transverse wave. This is going to be called a longitudinal wave because the wave will propagate horizontally from left to right, say, or right to left, and each little piece of medium is also moving in that same direction, left to right or right to left. And actually it's sort of easy to see in this case the coupling between the nearest neighbors. So each one of these sticks has a little white tip that glows in the dark, and it's pinned in the middle to make a pivot. And now if I hold this fixed and I hold this fixed and I move this one, it oscillates back and forth. So if this thing wants to stay equidistant between its two neighbors. So if I displace it so that it's not equidistant between its two neighbors, then a bigger and bigger force develops the more I displace it from that, and it oscillates back and forth. So we have things that individually, when their neighbors are immobilized, behave like oscillators. And then also, if I move this one, then its neighbor wants to move proportionally. So we have interactions between neighboring pieces. So now we have a medium in which waves can propagate, and the waves are going to propagate longitudinally, like that. And we'll see in another week, roughly, that this is what sound waves look like. So acoustical waves, sound waves traveling through air or traveling through water. In general, acoustic waves are compression waves, so the air becomes more dense, less dense, more dense, less dense, more dense, less dense, as the wave propagates that way. So this is actually a nice visual model that you can keep in mind for sound waves propagating through the air. If I just make a disturbance go from one end to the other, I'll just do a pulse. Gated pattern, but other. This machine. Now we have like a velocity or displacement node here, which corresponds to a compression antinode. And then we have a velocity or displacement antinode here. And you can see, again, the neighboring particles where we have maximum displacement. The neighboring particles are kind of staying a fixed distance apart at that point. So that's a compression node, but a velocity or displacement antinode. Notice that the place where you have a velocity node, also known as a displacement node, you have a compression antinode. So the place where the position never changes, or the velocity is always zero, is a place where the compression is varying most rapidly. And then if we go over here, where the position or velocity is varying most rapidly, see the distance between those two particles doesn't change. So that's a compression node, but a velocity antinode. This is a pretty good pattern. Well, so there's one velocity node. In other words, the velocity is always zero. There's a velocity node at the far end of the machine because that's clamped, it's immobilized. And that's kind of like what happens if you had a very massive wall at the edge of a room. You'll get a velocity node there. There's another velocity node about halfway across the machine. Velocity is always pretty close to zero there in the middle of the machine. But then you see halfway in between, let's say 3/4 away across the machine, you see a velocity antinode, meaning that the amplitude of the back and forth motion is very big. It's maximal. That's kind of neat because you can really see that they become more dense, less dense, more dense, less dense, more dense, less dense. So you can really see that longitudinal waves are like an oscillation of how close things are together, or like in air. You can imagine if you're talking about sound propagating through air, it's like a local oscillation of a little bit more dense, a little bit less dense, a little bit more dense, a little bit less dense. That's pretty decent. So you can see, in addition to the ends, we have two nodes, kind of at the 1/3 and 2/3 points.
We got antinodes at both ends.
Yeah, so it seems like we have a node in the middle, antinode. This is kind of like an organ pipe open at the two ends.
Yeah, that's two waves, right?
Yeah, it seems like there's kind of a node here, and there's kind of a node here. Yeah, but we have antinodes at the two ends at least.
And then three nodes, right? One in the middle.
Yeah, I think there's a node here, a node here, and a node here.
Yeah.
Yeah. It's pretty easy to show both transverse waves and longitudinal waves on a slinky. So here we can do longitudinal waves where okay, so I displace the slinky that way, left to right, and the disturbance propagates left to right. And then I can also do transverse waves on the slinky, so I'm going to displace the slinky toward you, away from you, toward you, away from you, and you're going to see the disturbance still propagate in that same direction along the axis of the table. I can make transverse waves with the slinky so I'm shaking the end of the slinky. Each piece of slinky is moving in this direction, but you can see the disturbance is propagating along the axis of the slinky. So okay, so those are transverse waves. Those are kind of like the waves on a guitar string. And then we can do longitudinal waves. So each piece of slinky is moving like this, and the disturbance is also moving like that. Yeah, that's pretty good. So these are longitudinal waves, which is more like sound propagating through the air. So all the action is happening along the axis of the slinky. Each piece of slinky is moving along the axis of the slinky, and the disturbance is moving along the axis of the slinky. Whereas this is a transverse wave, so each piece of slinky is moving perpendicular to the axis of the slinky, but the disturbance is propagating along the axis of the slinky. This is taking two traveling waves, two harmonic traveling waves in opposite directions, same amplitude, and adding them. And you see, when you add them, they make a standing wave. So this is one way to make a standing wave is you have a traveling wave to the right and a traveling wave to the left, both sinusoidal in nature. And when they overlap, you get a standing wave. That only works if they are the same amplitude. So I think what we're going to see next is the same thing we saw a moment ago, but I see one is positive, one is negative. This also works. So they have opposite, instead of having the same sign, they have opposite signs, but this also creates a standing wave. But then what you're going to see in a moment is if they have different amplitudes, then they don't quite create a standing wave. They create a wave that does a really weird kind of shuffle. It sort of goes, it's going to look as if it hesitates and goes and hesitates and goes and hesitates and goes. And I put the source code for these animations on the web page in case you're interested in how I did it with Python. So here you see they have different amplitudes. So you get this kind of funny pattern where it almost looks like a standing wave, but then it shuffles. So it kind of goes slowly, quickly, slowly, quickly, slowly, quickly. So it really does not make a standing wave. It makes a kind of funny, slip-sliding traveling wave. So to get a good standing wave, you have to have two sinusoidal waves going in opposite directions, same amplitude. So now this is the 1/2 wave fits on the string standing wave patterns. This is like the lowest mode for a guitar string. So here you see half of a wave fits on the string, emulating a standing wave. And then we're going to see the case where one whole wave fits on the string. Okay, here's one whole wave fits on the string. Now we're going to have 1.5 waves fit on the string. So you can see there's a node about 1/3 of the way across, and there's another node 2/3 of the way across. Now 2 whole waves should fit on the string. So you have nodes 1/4, 1/2, and 3/4 of the way across the screen. Oh, okay, so now we have 2.5 waves fit on the strings. There's 1, 2, 3, 4. Yeah, there are nodes at 20%, 40%, 60%, 80%. So that's 2.5 waves fit on the string. And now 3 full waves fit on the string. And I think finally this is all my program does. A moment ago we saw standing waves on the transverse wave machine. If I shook the end of the wave machine at just the right frequency, then we could fit exactly 1/2 wave on the wave machine, or exactly 1 wave on the wave machine, or exactly 1.5 waves on the wave machine. Here's an example of 1/2 wavelength fitting on the string if I have 2 ends of the string fixed. Here's 1 complete wave fitting on the string if I have the 2 ends of the string fixed. An integer number of half wavelengths fits on the length of the string. So usually we're interested most in the fundamental mode where a half wave fits on the string. What you actually get if you pluck a guitar string might be some mixture of the fundamental mode and its overtones. You know, what we hear the most is the fundamental mode. From string to string we're going up in pitch on the fundamental mode. And you you'd say, what accounts for that? The possible frequency, so n equals 1 in that equation I wrote down there is the fundamental mode. The fundamental mode will have a higher frequency if we make the tension in the string higher. The fundamental mode frequency is lower if the mass per unit length of the string is bigger, because the mass per unit length of the string is downstairs. And you can see that on a guitar from the fact that the lowest frequency strings tend to be made of much heavier material, and the highest frequency strings tend to be made of much less heavy material. So the diameter of the string is bigger here, so it's a bigger mass per unit length. This is a smaller mass per unit length. So the mass per unit length is a property of the string material. Say, okay, I'm picking a kind of string, so that has a certain mass per unit length. So now you just have that one factor of L downstairs outside the square root. So you say, if I make L smaller, the resonant frequency should become higher. And I think you can see that happen. Again, I'm going to try to play a major scale. Let's see. So what I'm doing is I'm going up is I'm making the length of the same string smaller and smaller. And by making the length of the same string smaller and smaller, I'm making that fundamental frequency for what's left of the string bigger and bigger because that length is downstairs. I can also show you what the tension does. I'll do that with a real cheapo guitar here. Take the same string and let's increase its tension. It seems as if I'm decreasing its tension here. Let me go the other direction. I'll increase its tension. Okay, so increase the tension, the fundamental frequency goes up. Decrease the tension, the fundamental frequency goes down. Now those are frequencies you can easily hear. They're kind of in the hundreds of hertz. Let's go to a frequency that we can see, or almost see. So right now you're looking at this piece of string. I actually measured out pretty approximately because I just used a kitchen scale with a few meter length of string, but I measured the mass per unit length of this string to be about 2 grams per meter. I took a 3-meter length of it, and my kitchen scale said 6 grams, but it might have been 5.5 or 6.5. So we know the mass per unit length roughly of this string. So I'd say like 0.002 kilograms per meter. What's the tension of this string? So to fix the tension of this string, we took some little weights, and we're dangling little weights from the end over here. So we have some little weights that look like this. These are calibrated. This one is 200 grams. That's 0.2 of a kilogram. We have a total mass on the end of this string of 400 grams, which is 0.4 kilograms. If you multiply that by little g, 9.8, you get roughly 4 newtons, just a little under 4 newtons. The tension is about 4.0 newtons. The mass per unit length is about 0.002 kilograms per meter. And then I measured out the length of the string. The length of the string turns out to be about 1 3/4 meters. Okay, so we get about 1.75 meters for the length of the string. And if you plug all that stuff in, I worked out that the fundamental frequency, so that's where n equals 1 in that expression, should be about 12 or 13 hertz cycles per second. So right now this string is shaking up and down at about 2 hertz, 2 times per second. So I'm going to dim the lights so you can see the string a little better, and then I'm going to tune the frequency until you see very clearly that 1/2 wave fits on the string. And then we'll go up when we'll look for the other modes. Well, I'm going to gradually increase the frequency. That's 4 cycles per second, 4 hertz. There's 5 cycles per second, 5 hertz. There's 7, 8, 9, 10 cycles per second, 11. Okay, now 12 or 13 was my prediction from the input numbers. There's 13, but it seems that it actually wants to go just a little bit higher than that. I got about 15 a moment ago. That's too high. Oh no, that's pretty good actually. Yeah, that's actually pretty decent. Okay, yeah, so that's 15.2. If we go a little bit higher, see, that's not so good. And if we go a little bit lower, that's also not so good. It seems like right around there seems to be the most obvious standing wave, where you see half a wave on the string. So yeah, so that looks pretty decent. So now the next frequency where we should be able to get a pretty dramatic effect is twice that. So this is 15.2. So if we go up to 30.4, we should see a pretty good standing wave, but instead of half of a wave on the string, we should see one whole wave on the string. Let's see that. Okay, that's 30.6. So that's pretty good. So now you see a pretty convincing one whole sine wave on the string. So that's 30.6 cycles per second, 30.6 hertz, roughly double the 15.2 we saw a moment ago. So now the third mode should have 1.5 waves on the string. So that should be at triple our original frequency. So that should be about 45.6, maybe 45.9, somewhere between 45.5 and 46 cycles per second. Let's try that. That looks pretty good. That's 44.6. Let me see. 44.7, 44.9, somewhere in that range. Okay, pretty close to 45 hertz. We see a pretty nice convincing 1/2, 2 halves here. So to the end, that's 1/2, and that's 2 halves, that's 3 halves. So we have 1.5 waves fit on the string. Remember, because a sine wave goes like that. And let's do the next one. It should be around 60 hertz. I think as we go to higher and higher frequency, the energy is dissipated into friction more and more quickly, so it becomes harder for us to excite the string. This is pretty decent. That looks like 2 whole waves. So there's the end. There's a half wave. There's 2 halves. There's 3 halves. There's 4 halves. So 2 whole waves at 60 hertz. Let's try the next one. So the next one should be around 75. This was 57.3. Oh, hey, that's actually not bad. Oh, that's close. I think that's pretty close. Let's see. That actually looks pretty good. So there's the end. There's 1/2. There's 2 halves. There's 3 halves. There's 4 halves. 5 5 halves. Okay, so we got 5 half wavelengths at, this was 71.8 hertz. I think that's probably going to be the best we do. Let's see. Okay, so then we want to go up close to 90. I grew up in Boston, so I say 90. So well, that's pretty good too. You can kind of see that. Gee, this is working better than I expected. Okay, so at about 86.1 hertz, we see there's 0, there's 1 half, there's 2 halves, there's 3 halves, 4 halves, 5 halves, 6 halves. Pretty decent. So we need 3 whole waves fit on the string there. Pretty good. Let's go back to the 13, 15-ish, 15.2 I guess was our fundamental mode. Yeah. Okay, now if we double the tension, keep everything else fixed, then we should increase the fundamental frequency by the square root of 2. So instead of being around 15 hertz, it should be like around 21, 22 hertz. So let's try that. So again, if we go from 400 grams, 0.4 kilograms, to 800 grams, 0.8 kilograms on the end of the string, then I claim instead of 15 hertz, we should see something, well, 15 times square root of 2 is 1.414 roughly. So that's going to be a little less than 22 hertz. Let's try that. I can add over here. So we have 400 grams now. Here's 2, 3, 4. So there's another 400 grams we'll add to it. So now we have 800 grams over there. So now we should see, so we just doubled the tension. And because of the square root, then we should see about 40% higher, 1.4 times for the fundamental frequency. So I claim it's going to be around 21, 22, 15, 16, 17, 18, 19, 20, 21, 22, seems like, let's see, where do we get, well, that's pretty nice. Okay, 20.5 is where I get the nicest response there. So yeah, that's pretty decent. Okay, so we went from 400 to 800 grams. Now let's go from 800 to 1200 grams. So that's going to be 3 times the original tension. Square root of 3 is about 1.7. So it should be 1.7 times the original fundamental frequency. So it should be about 26 hertz. So we should see a fundamental frequency of about 26 hertz if we add this additional 400 grams of mass to the end there. Let's see what happens. I've never tried this before. Okay, so I expect it to be something like 26 hertz. I haven't peeked yet to see where it is. Let's see where it is. 25.2. Hey, that's not bad. So 25.2 hertz is where we get the really nice fundamental mode response. And then again, okay, there's 25.2. So if we go to about 50 hertz, we should see a whole sine wave here. 50.4, we see a whole sine wave, very nice. About 74 hertz, we see 1.5 sine waves. Okay, so you get it, you get the picture.